final ID1 minus ID2 versus V in has a third order coefficient and is responsible for third order intermodulation. So is there some intuition about it?
So the recommendation is to have overdrive
larger, yes.
larger force.
Yes, that's in general. But my question is more philosophical. I'm saying if it's just square law, why are we producing third order? Sorry?
Because of the mathematics.
Yeah, but is there an intuition? Well, actually, there is some. We can make some, we can have an intuitive view of it because it's true. It's a square law. But if we because when one thinks about differential pair, thinks about actually is used to think about a linear behavior. So thinks about a virtual ground here. If these were true, then we should really be surprised about IIP3. But think about it in a different way, because when we involve IP3, we're thinking about something which is not anymore under small signal operation. We are on large signal operation. So let's assume this difference is large. What's happening is that this node is not anymore a virtual ground. This is, on the other hand, following the gate or the device which is driving. So when this is high, this node is following. When this is high and this is driving, this node is following. So we have this node which is moving at twice the frequency of the input signal. So this node actually is not a virtual ground under large operation, but it's doing a rectification. So it's true that the original device is described by a square law, but this square law doesn't apply, or applies, but of course gives a different result if the source is moving and is a function of the input voltage. So this makes things much more complicated, and the actual relation input-output is not anymore described by a square law, but by a polynomial, because this is a function of the input voltage. So if you develop it, you find a polynomial again, which justifies a third order intermodulation. Okay? But if we were freezing this node, as you can do in a pseudo-differential circuit, let's assume you use a mirror to bias the circuit and you freeze it to ground. Then it's really a square law and you do not have any IIP3. Okay? Sure.
For deep side micro technologies, if we increase the overdrive voltage, the transistor for direct velocity saturation region, as a result, the square law is not.
That's true.
So if we work with deep side micro transistor, do we still have, since it's a somewhat linear?
Yeah, you're right. It's a more linear relation. You tend to be more linear, but still you have third order intermodulation.
So it is still true to have larger VDS sets for deep side micron too.
Yeah, I would say also that with this one micron, the device is naturally more linear. So you suffer a little bit less. So you go in that direction, you suffer less, you find a compromise between the problem you say and.
Because large VDS sets trade with the large current, right? You have to reduce the W to have, or the aspect ratio to have.
At the same time, the device is more linear. So the two things are going in the right direction for you. So more or less doesn't change much. The device is more linear, but you need to be more careful. Do we have some more time? 10 minutes? VGS 0 means the biasing. So means when everyone drives ISS over 2. Okay, as I said, I do not make any calculation here, but what we can say is that if it's still square law and we freeze the two sources to ground, then we expect to have much better linearity under IIP3 respect. And we also have voltage saving than a differential pair. This circuit suffers from a second order intermodulation that we'll see later. Everything is coming later. Okay, so one way to, for example, to improve the linearity of a differential pair is introducing a resistor. There are many ways to do it. So I wouldn't even say that this is the most common. Again, as an example, if we put a resistor between the two sources, then we improve the linearity of the differential pair, and the expression corrected by the presence of Rs is given by this equation, okay? So, of course, it's intuitive. The more Rs, the better it is in terms of IIP3.
The concept is different from having the source to the abstract.
Yes, it's
You
different.
know the linearity because you have the linear element.
Yes, it's different. Okay, much in the same way, we can characterize the second order intermodulation of a circuit. I wouldn't spend much time because once that principle is understood, then it is also second order intermodulation, because basically we have, due to the second order term, some components that grows which are proportional to omega 1 minus omega 2 or omega 1 plus omega 2, which is basically the same coefficient, and grow with the second order coefficient of A. So if we draw in a plot in a log-log scale, we have the linear component and the second order intermodulation. They meet each other at a point where the corresponding amplitude is called IIP2. And this is an important metric in direct conversion architecture. It's not much important in super heterodyne, in heterodyne, but it's important in direct conversion architecture. Why? Basically because when you generate second order components, think about the sinusoid, any frequency. If you square it, you produce a component which is proportional to the second harmonic and also has a DC component, okay? Correct? So sine of omega 1 t is sine square, which means 1/2 plus 1/2 sine 2 omega 1. So this 1/2 is at DC. So if my goal is down-converted the signal to DC, which is direct conversion from antenna to DC, any second order nonlinearity is also producing something at the same frequency. So it's a problem. If I have an heterodyne architecture, which means that I have a step intermediate, then whatever I'm doing before this intermediate step is still going to baseband, and it's not a problem in the band of interest. So for a direct conversion, it's a problem. For a super heterodyne, it's not. But I would say that nowadays, 0. Okay, this is the actual expression of the thermal noise of a device. Then we can demonstrate then that this is, especially in a long channel device, equivalent to the GM of the transconductance of the device itself. Plus we have a 1RF noise component, which means that when we look at the energy of the noise close to 0, we find an increasing energy. And this is described by this component 1RF. So I just remind you this noise expression because we will use it to determine the quality of alternative amplifier and mixers. Then you can have also, and I added here, a resistive component that in a MOS device can be associated, for example, to a real resistive term, the polysilicon and whatever. In a bipolar device, it's more fundamental, is more related to the physics of the device, whereas in a MOS, it's only the parasitic of the gating access. Now, and then maybe we can break. Just the definition of noise factor and the implications. So the noise factor is defined as the ratio between the signal to noise at the input of a circuit over the signal to noise at the output of the same circuit, okay? Which means that F, the noise factor, represents how much a system degrades the signal-to-noise ratio. Or looked at in another way, we have a signal at the input that has some signal-to-noise ratio. So the signal is accompanied by some noise, and we have a relative difference in power between the two quantities. Now, what we want to know is what's happening to this ratio due to the circuit under my control, under test. So the noise figure or the noise factor determines how much noise the circuit is introducing and how much the circuit itself is degrading the signal to noise. So, of course, due to the definition and my inspection, you can conclude that if the signal to noise ratio at the input, well, if the circuit is not contributing any noise because it's an ideal noiseless circuit, then the input and output signal to noise ratio are equal, and then the noise factor would be equal to 1. So noise factor equal to 1 or 0 dB in decibels is the minimum theoretical noise factor or noise figure that we can find. Okay, it can seem, especially for, when I was a PhD student, I was not involved in IC design. I was involved in more discrete component activity, still design, but of amplifier for very low noise application for, at that time was for physics experiments. I worked a little bit didn't work. I was as an intern at CERN. And so when you design amplifier in that framework, you are really interested to achieve the minimum noise you can, and you never use a noise factor, noise figure as a metric. You're just interested in the minimum noise, the minimum. I mean, you are eventually, when you do charge amplifier for those applications, you usually talk about electrons of noise. So, so you're counting the electrons equivalent of the noise. So going to this rather strange noise factor or noise figure can eventually seem unusefully complicated. So one can wonder, why should we use noise factor and introduce it? Especially if I now add this observation, which is, for example, that if the input signal of a circuit is noiseless, so let's assume we do not have any noise at the input, because I said in the definition, signal to noise ratio at the input, which means there's some noise at the input. There can be a system where you do not have any noise at the input. So if you do not have any noise, what you conclude is that signal to noise ratio at the input is infinite. So the noise factor of the circuit is infinite by the mathematics, okay? Which is surprising and at the same time justified by the fact that the system doesn't have an internal source of finite noise, okay? But in telecommunication, which is true, for example, in sensors or this kind of charge amplifier for minimum noise. But in telecommunication, whenever you have an antenna, you always have associated a dissipative, resistive component, which determines noise. So in at RF, the antenna radiating is noisy, and the signal to noise ratio at the input is finite, which makes which makes the definition meaningful, and using it something which defines the circuits and the different blocks. Do you want to break, or shall we go another 5-10 minutes? Break? Break. Okay. Sure. Sure, sure. That's an alternative. Yeah, that's an alternative. Sorry?
Regarding my earlier question, I was trying
Yes.
to be...
Merhabalar hocam. Bu 5 günlük çalıştayla ilgili neler düşünüyorsunuz?
Şimdi bu çalıştay radyo frekanslı tüm devre tasarımı konusunda Türkiye'de düzenlenen ilk çalıştay. Hatta daha ötesi tüm devre tasarımı konusunda düzenlenen ilk çalıştay. Tüm devre konularını bundan yaklaşık 40 yıl önce İstanbul Teknik Üniversitesi'nde başlattığımızda teknoloji de bilgi düzeyi de bugünkten çok daha gerideydi. Bugün gelinen noktanın geçen 40 yıl içindeki muhteşem gelişmenin bu tür çalışmalarla genç nesillere, genç tasarımcılara, genç akademisyenlere yansıtılması ve bunların birlikte tartışılması çok güzel bir durum. Ben bu çalıştayın Türkiye'de bundan sonra yapılacak olan benzer üst düzey çalışmalar için çok önemli bir başlangıç olacağını ümit ediyorum. Bu çalıştayın bir başka önemi de organizasyonun Türkiye'nin birkaç üniversitesinin, işte Işık Üniversitesi, İstanbul Teknik Üniversitesi, Boğaziçi Üniversitesi ve İstanbul Üniversitesi'nin ortaklaşa düzenlediği, ortaklaşa başlattığı bir aktivite olması. Bu sefer Işık Üniversitesi'nin ev sahipliğinde yapılan bu toplantının demin de söylediğim gibi gelecek yıllarda daha başka ortamlarda, daha geniş katılımlarla tekrarlanacağını umuyorum ve böyle olacağına da inanıyorum.
Bugün bizim için çok önemli bir gün. İstanbul'daki 4 üniversitenin bir araya gelerek organize etmiş olduğu uluslararası bir çalışma grubunu sizlere tanıtmaktan mutluluk duyacağız. Geçtiğimiz sömestr, bahar sömestrinde çok değerli hocamız, konusunda dünyaca ünlü Profesör Doktor Franco Maliberti, İstanbul Teknik Üniversitesi, Boğaziçi Üniversitesi, İstanbul Üniversitesi ve Işık Üniversitesi'nin birlikte organize etmiş olduğu elektronik kırmık tasarımı, çip tasarımı veya entegre devre olarak halk arasında bilinen tasarım dersini vermek üzere aramıza katıldı. Bu 4 üniversitenin sponsorluğunu bu vesileyle Işık Üniversitesi üstlenmiş oldu. 4 üniversitenin de önde gelen öğrencileri buna katıldılar. İstanbul Teknik Üniversitesi'nden Devrim Akşin, Türker Kuyel hocalarımızla, Boğaziçi Üniversitesi'nden yeni bu konudaki fevkalade değerli, dünyaca tanınmış arkadaşımız Profesör Doktor Günhan Dündar ve İstanbul Üniversitesi'nden ben bölüm başkanı olarak Sıddık Yarman ve aynı zamanda Işık Üniversitesi'nden ben ve bölüm başkanımız Ahmet Aksen ve dekanımız Profesör Doktor Yorgo Stefanopoulos bu dersin organizasyonunda önemli görevlerde bulundu. Esas önemli olan İstanbul'daki bu 4 üniversite hiçbir önyargısız olarak, hiçbir beklentisi olmadan sadece üniversitelerimizde okuyan gençleri dünya rekabetine uydurabilmek amacıyla elektronik endüstrisine tasarımcı yetiştirmek amacıyla bir araya geldiler. Ve bugün de yine uluslararası düzeyde bir workshop başlattık. Şimdi bu 4 üniversitenin hocaları ve Franco Maliberti bizlerle sıradan kendilerine bu konulardaki düşüncelerini soracağız. Okay, Franco, here I am. First of all, we'd like to appreciate what you have contributed to our 4 universities, to our students in electronics engineering. You taught an outstanding course last term here. What was your impression regarding the Turkish students, regarding the quality of the course?
Yeah, we had a very interesting course and very good student. You know, the attention of student was very high, and I was impressed on the background level of the student. They made a lot of questions. They had good participation to the classes, and I was very happy to be here. So I think that with this kind of student, you can have interesting result in the microelectronic area.
You think that Istanbul, as a center of students, is going to be able to provide top-notch, high-quality engineers, electronics engineers, IC designers to the whole world, all the way from Istanbul? You believe in that?
Yeah, of course. You know, if you have a good student and you have people with a lot of enthusiasm, I think that that is the main basis. And also, I have seen that, you know, these universities, you know, Boğaziçi, E2, and also ISIC, they have a very good basic courses. So the background knowledge is the right one, and I think that you can have excellent result for creating the boundary condition for economy based on integrated circuit design and application of these things.
Okay, now I'm going to kind of request from Professor Günhan Dündar, whatever you said, to translate your feelings, and also I'm going to ask him, sevgili Günhan Dündar'dan rica edeceğim, bu güzel ortak çalışmadaki duygularını bizlerle paylaşmasını.
Teşekkür ederim. Profesör Maleberti burada olmaktan çok mutlu olduğunu söyledi. Öğrencileri hem ilgisini hem de bilgi düzeyini çok beğendiğini ifade etti. Daha sonra sizin sorunuzda Türkiye'deki mikroelektroniğin geleceğiyle ilgili bu öğrenci düzeyiyle parlak bir geleceğin bizi beklediğini ifade etti. Kendi duygularıma gelince ders benim için çok ilginçti. Yıllardır ders veriyoruz ama ilk kez birçok üniversiteden öğrencinin olduğu bir dersti. Ve dersi hem Profesör Maleberti gibi bir hocayla hem de Devrim Hoca ve Türker Hoca gibi çok sevdiğim meslektaşlarım, arkadaşlarımla beraber vermek çok güzeldi. Ders bence çok başarılı oldu. İnşallah devam ederiz diye düşünüyorum.
Çok teşekkür ediyoruz sevgili Günhan. Evet, Devrimciğim sen bu konularda da gerçekten öncülük yaptın. Türker'le beraber teknik üniversiteyi bizlere açtın. 4 üniversiteyi, İstanbul Üniversitesi, Boğaziçi Üniversitesi, Işık Üniversitesi ve kendi üniversitenin öğrencilerini hep bir araya getirdin. Bu konudaki görüşlerini, düşüncelerini bizlerle paylaşır mısın?
Öncelikle Işık Üniversitesi'ne ve size çok teşekkür etmek istiyorum üstadım. Çünkü bizler katalizörüz, fakat esas materyal olmasa, bir arkamızda güç olmasa bunların gerçekleşmesi imkanlı olmazdı. Bu geçen dönem verdiğimiz dersler ve şu anda workshop'la devam eden aktivitenin esas amacı şu: Türkiye'de insan kaynağı olarak, bilimsel yetkinlik olarak çok ciddi bir potansiyelimiz ve altyapımız var. Fakat bununla ilgili bir liderliğe ihtiyacımız var. Bu liderlik, bu potansiyelin ve altyapının ekonomiye katkı sağlayacak startuplar, şirketler paraya dönüştürecek bir yola girmesi. Şimdi bu workshoplar ve bu çalışmalarla temel amaçladığımız şey, Türk bilim insanının, Türk mühendisinin dünyada yapılan işlerden haberdar olması, bunlarla ilgili çalışması ve bunlarla ilgili üretim yapması ve bunları geniş bir perspektifte bütün Türk elektronik endüstrisine yayması ve bunun sonucu olarak da ekonomimizin 4 trilyon dolarlık muazzam bir pazarda ciddi bir pay sahibi olması. Bu konuda işte Aselsan'ın, mikroelektronik şirketinin, Işık Üniversitesi'nin, İstanbul Üniversitesi'nin, Boğaziçi Üniversitesi'nin, Pavia Üniversitesi'nin, Doktor Maleberti'nin çok ciddi katkıları oldu. Kendilerine çok teşekkür ediyoruz ve bu katkıları devam etmesini bekliyoruz. Umarım bu yolda daha emin adımlarla, daha büyük adımlarla ilerlemeye devam edeceğiz.
Çok teşekkürler Devrim. Sevgili Türker, sen Teksas'tan geldin. Devrim'le Amerika'da birlikteydiniz. Texas Instrument firmasında da çalıştınız. A&M'de doktoralarınızı yaptınız. Eşini Amerika'ya gönderdi. Sen burada kaldın. Bu derste de çok güzel rol aldın, hocalık yaptın. Düşüncelerini bizle paylaşır mısın?
Hocam ben öncelikle size, Franco'ya, Günhan Hoca'ya ve Devrim Hocamıza çok teşekkür ediyorum. Böyle bir organizasyonun olması Türkiye'de çok önemliydi ve çok ileriye doğru atılmış, çok sağlam bir adımdır bu. Ben İstanbul Teknik Üniversitesi öğretim üyesi olarak değil de o şapkamı çıkartarak endüstride hayatını devre tasarımından kazanmış bir insan olarak bir yorumda bulunmak istiyorum. Biz bu alanlara girmeliyiz. Ve büyük hızla girmeliyiz. Çünkü karşılaştıracak olursak Türkiye'de bazı şirketler var. Bu şirketlerde 50 bin kişi, 70 bin kişi çalışıyor. Ve bu şirketlerin belli bir gelirleri, belli bir karları var. Aynı karın benzerini Amerika'da yüksek performanslı devre tasarımı yapan 300-400 kişilik şirketler yapabilecek durumda. Şimdi böyle olduğu zaman bu çok karlı alana, çok yüksek performanslı devre tasarımı alanına ilk defa çabucak girebilmemiz için eğitimler, seminerler, konferanslar, startup şirketler ve bu yoldan başarıyla çok büyük hızla ve bilinçle ilerlememiz gerekiyor ve tekrar teşekkür ediyorum buna ön ayak olduğunuz için.
Çok teşekkürler sevgili Türker. Evet, Şebnem Hanım burada. Şebnem Hanım Işık Üniversitesi Uluslararası İlişkiler Ofisi'nin yöneticisi. Bu konuda Işık Üniversitesi'nin uluslararası düzeyde yapmış olduğu çalışmaları bize anlatır mısınız? Bakın burada sürekli eğitim merkezinin oluşturulması, özellikle ileri teknolojileri içeren, elektronik entegre devre tasarımını içeren bir faaliyet başlattık. İlk örneğini de şimdi veriyoruz. Siz çalışmalarınızı bize kısaca anlatır mısınız? Bu konuda Işık Üniversitesi'nin nasıl destekleri olabilecek bize özetler misiniz? Bunu hem de mütevelliyeti başkanınız olarak soruyorum size.
Tabii ki. Işık Üniversitesi uluslararası platformda saygınlığını gittikçe arttırmaktadır. Ve Erasmus öğrenci sayımızdaki artış da bunun göstergesidir. Hem giden öğrenci hem gelen öğrenci sayısı. Bu tür platformlar da bizim uluslararası platformda tanınırlığımızı arttırmaktadır. Dolayısıyla çok önem veriyoruz bu tür organizasyonlara. Örneğin şimdi Dr. Maliberti ile görüştük, bir ikili anlaşma yapmak konusunda. Dolayısıyla bu tür organizasyonlar özellikle bilgi alışverişini sağlaması, dediğim gibi uluslararası tanınırlığımızı arttırması sebebiyle bizim de özellikle üzerinde durduğumuz ve destek verdiğimiz çalışmalardır.
Çok teşekkürler Şebnem. Değerli izleyiciler, zil çaldı. Biz çalışma grubuna hemen katılmak zorundayız. Hepinize sevgiler, saygılar gönderiyoruz Işık Üniversitesi'nden. Hoşça kalın.
Teşekkür ediyoruz.
So the input signal to noise ratio, if we have an input voltage source VIN and we assume that the noise is due to the source resistance of the antenna, so we call it V square N RS, and is given by 4kT RS, it's thermal noise associated to the resistor, we can say that this is the signal to noise ratio, Vin square over V square RS. You see multiplied by alpha square and alpha square, where alpha is the partition at the input, made of the input impedance and the resistor RS. This is just not to be careful not to make confusion between the actual gain from the input source and the open loop gain or the gain, the intrinsic gain of the circuit we are analyzing. So we call one AV, the intrinsic gain, so that the overall gain is alpha AV, also named A0. Anyway, we'll see later on. So V in over V square RS. At the output, the signal will be V in square times alpha square. We are talking about RMS values. We are dealing with powers in some way, because we're then adding up random signals. So we always talk about RMS signals. So everything is squared. Transfer function are squared, gain is squared. So V in square, alpha square, AV square. This is the output signal over the output noise, V square RS, alpha square here, times the gain, AV square, plus V square N. What is V square N? We assume to have the noise of interest under attributed to the circuit at the output of the circuit itself. So looked at in another way, once we know what is the output noise produced by a circuit, we call it Vn, And this will be the basis in the future calculation to determine the noise figure of any circuit. So again, we attribute all the noise of the circuit at the output through this voltage source V square N. So we say the signal is V in square, alpha square, AV square, and the noise adds up, the noise over S plus the noise of the circuit, okay? So now it's only calculation. So NF is the ratio between this quantity, sorry, it's gone. Battery are gone. So we input signal to noise ratio over output signal to noise ratio. So we just write V square RS as 4kT RS, and we go on with this, elaborating this expression. At the very end, we have 1 plus V square N over alpha square AV square 1 over V square. We group everything under V square RS, so 4kT RS, and we find what? We find alpha square V square RS plus V square N, which is the output noise. So from this expression, we have that the noise figure is 1 over 4kT RS times what? Times the output noise over alpha square AV square, which is the overall gain from the input to the output. So this expression, or this calculation, starting from an input source, which is the antenna, with noise associated to the resistor, and the noise of the device is all contributed by a signal source in series with the output and called Vn, tells us that the noise figure in this condition is given by the output noise, RMS, over the gain from the antenna, from the source to the output, normalized to the noise of the resistor RS. So this is interesting because now, whenever we have a circuit, we just calculate what is the noise at the output. If we know the gain, we already have the noise figure. Okay? Okay, so given this tool and introduction, let's go a little bit more, give more insight into the noise figure under another perspective, which is probably more interesting from a communication point of view. So this is the definition, signal to noise ratio at the input over at the output. We can rewrite it as power of the signal over power of RS, of the noise due to the resistor RS, divided by the output signal to noise ratio. So let's write it in a different way. So we can say that the power of the signal will be equal to the power of the noise power, the resistor RS, times NF, times the output signal to noise ratio. Okay? Now, of course, this is a power spectral density. So this will also be a density. So to go to a power in dBm, to the actual integrated power, we just multiply the second term by B, the bandwidth, and we'll have the total power at the input is related to the noise power times density, times the bandwidth, times the noise figure, times the signal to noise ratio at the output. So written in dB means that the input power is equal to the power spectral density of resistor RS plus the noise figure plus the minimum signal to noise ratio plus 10 log of the bandwidth. So this is a very interesting equation because it tells us what is, for example, the sensitivity of a signal once we know the minimum signal to noise ratio, which translates in other terms in the maximum noise figure we can tolerate from a receiver. So let's look in another way. We, for example, know that the application we're interested in requires a given signal to noise ratio to elaborate the signal through the processor with a given bit error rate. So we know from the specs what is the signal to noise ratio. For example, in a typical QPSK for wideband CDMA, which uses, again, a QPSK, an alternative version of QPSK, the signal-to-noise ratio, when we enter into the digital processor, is also called as AB over N0, is 7 dB, just to have an idea. Once we know this ratio, we can also know, because we know the bit error rate, so the bandwidth, we can also determine the sensitivity, because this depends on how low we can do the noise figure of our receiver. So whenever you see two competitors, you see that it's not enough being able to meet the sensitivity requirements of the spec, given to have the product allowed to be a commercial product. Because two different manufacturers will tend to fight about the sensitivity they can achieve, because this ultimately depends on the noise figure of their transceiver. So the battle is in reducing this number. And if you go and you look at the specs of telephones, you can find that there are some difference between, maybe you are not enough to decide to buy one or the other, because there are other things that matters, such as the design. But still, if you look carefully, you see that there are different. For example, Nokia was, in my opinion, one of the best in terms of sensitivity for GSM and whatever. In fact, was a very good quality. I'm not saying the other are not. Anyway, the technology of Nokia has always been very advanced. For example, the iPhone has many other things, but uses a very old technology. Doesn't have inside much new ICs, but has a very good design approach, many chips, and so integration is not a big problem, because they are betting on other things. So we can further simplify this equation, saying that the sensitivity is equal to minus 174 dBm per hertz. Why is a number coming out? Because I'm assuming RS of 50 ohm. So if RS is 50 ohm, and you calculate 4 kT RS, this density in dBm is equal to minus 174 dBm per hertz. So we know the bandwidth. Well, depending on the application, we know the bandwidth. We know, given the modulation, what is the minimum signal-to-noise ratio to go into the baseband processor. And so what we need to do is reducing the noise figure as much as we can. And this is something you do as an analog designer, and this is really your job. So also, we can also understand from these three contributions that are known altogether noise floor, that, for example, the sensitivity for a given signal-to-noise ratio depends on the data rate. So knowing that a given application has some sensitivity doesn't immediately mean that if the applications are different, that a better sensitivity, a lower sensitivity reflects into a better product, because it depends on the application for which it's done. So, for example, GSM, which has a low rate, will probably have a sensitivity which is much lower than a wireless LAN or every wideband application, because the bandwidth increases, and immediately for the same noise figure, the sensitivity increases. But that's only an apparent disadvantage. Okay. Or even more, we can say that if we have big or wide data rate, we cannot expect to cover wide areas. In fact, wireless LAN are working usually in a local area. If you want to transmit, well, either you use a much higher power, or you don't know what to do. In fact, that's something interesting. I can just to break the lecture for 1 minute. For example, now that you see this really wideband portable stuff, such as iPad, and those new tools that are communicating really at a fast pace with huge data exchanged, the question is, how can I make them efficient? How can anyone communicate wherever he is? Because the rate is huge, is wide. And I would like everyone communicating wherever he is. So I would like everyone using a base station so that he can download information, not just in a wireless LAN, in a local area network. So the point is that in a couple of years, I've been in touch with the company, and I expect in a couple of years, having everywhere many more cells, instead of only one base station in some kilometers, you will see so-called small cells that will be applied everywhere. For example, where you have lightning in the cities, and these will receive your signal, your wideband signal, and will transmit that signal to the base station. So you will have an intermediate hub, which is not present today with lower rate communication, but will be, the infrastructure is being built, in a couple of years will be there, because of the advent of this iPad and all this big and massive data needed in the communication. And one of the communication, because it's still wide bandwidth, we're talking about gigabit per second in some hub and application, one of the technology that might take advantage for the communication between the general hub and these small cells that will be everywhere on the light, this probably will be 60 gigahertz. There's this possibility. Okay. Okay, so this is it. If you have any fundamental question about intermodulation, noise, now is the moment, because then we move to transceiver architectures. And I will use the concept we have developed, but will not go back into the fundamentals. So if you have any question, yeah.
I have one question. Can you go one slide? Well, for this noise floor, we have one fundamental limitation. We cannot go below -174 dBm.
Yes.
And of course, it is because like 50 ohm standards that we use in the measurement equipment or electronic equipment. Do you see any possibility to decrease it for lowering of this noise floor even further? Why not 1 ohm?
Yeah, in principle you can. You know, well, it's a very smart question. In principle you can. In practical, I don't think you have much margin. So let's say that for every application you can have in mind where you have massive commercial products such as at RF, I think the limitation is not only the measurement equipment, but probably the major point is the commercial components that are off chip. For example, think about the SAW filter that is placed between antenna and chip. That one is a commercial one, and that requires 50 ohm as a load and as a driver. So if you don't have 50 ohm, those are not working properly. So this is the main reason why you usually design for 50 ohm at RF. What you are saying is actually true if you're, for example, thinking about a 60 gigahertz system, where one, the interferers are much less important, so you can do everything on chip. So you can have the antenna on chip, the chip itself, and you have no interface. Everything is under your control, then you could do it. We made some work on that, but then we discovered that at the very end, when you try to go to the minimum, which is, at the end, the minimum noise is given by the ratio between the voltage series source of a device over the current, the parallel current. That's the optimum noise, the optimum noise resistance. It's not much different from the resistance you at the very end have in the antenna that is receiving. You can improve something, but we tried, but not much. Well, a factor of 1.5, 1.3, but not much more. But that's, in my opinion, 60 gigahertz or where you have everything under control. At RF, where you use external components, off-chip components that are not under your control, you cannot. Because otherwise, for a company, its transceiver wouldn't be compatible with the others.
The answer, in my opinion, whenever you talk about 50 ohm, here's the antenna, here's the amplifier, right? Actually, there are two fixed impedances here. The input impedance of the amplifier, which is the input impedance of the transistor wherever you see. On the other side, you have the antenna impedance. Nevertheless, as far as noise pure computations and calculations are concerned, you have to consider the input of the transistor to match to the antenna by means of the matching method. So in this case, the best solution can be obtained when the input impedance of the transistor is conjugated to match to the
Yes.
Antenna. Therefore, your optimum perfect noise resistance, or resistance, I mean the impedance that you're going to be seeing on your source side, which is the front end of the amplifier, is going to be complex conjugate of the input impedance of the transistor. Therefore, the real part of the impedance of your source is going to be the real part of the transistor. Therefore, for the best computation, the real part of the input impedance, the real part of the transistor should be taken into account. Whatever it gives you, then you're going to have over the bandwidth, you're going to calculate this.
Yes, but actually that's from if you have everything under your control. But the point is that if you are in a commercial application and you have a SAW filter in between the antenna and the chip, and that one needs to see 50 ohm. So whatever you do is 50 ohm for that. In principle you can, but not at RF. No company would listen to you if you don't do it 50 ohm.
It's a big discussion. Actually, this is not a wise idea because the chips are the chips. The input impedance of the transistors cannot be changed. What are the CMOS technology that you're going to use, or what are the technology that you use? The smart, I mean, in the past, always the engineers, they don't know what they are doing. They say, okay, I'm going to match it to 50 ohm, it's standard. Why is 50 ohm? If you go back to the 1940s, you're going to come up with 50 ohm characteristic impedance of the transmission lines. But what to do now, instead of using, so you're going to match your antenna to 50 ohm, and there will be a discrepancy in your matching network over the frequency band. Then you're going to match the input impedance of your transistor to 50 ohm, there will be another mismatch. Then you're going to put those two matching networks together. You're going to put two designs, you see. So in this case, it's better not to think in terms of 50 ohms over a wide band design, directly measure the input impedance of the transistor and match the other. I'm sorry. So that's the way it is. We're doing the designs in this way. Francesco. Of course, it depends. If you're not doing the commercially off-the-shelf components, because if you are buying an amplifier with 50 ohm input, this is some different story. But if I do everything starting from the chip, then I have my antenna, I design it, I have my chip.
But then you need also to design the filter.
Yes, to it is.
Yeah.
Otherwise, you lose a lot in the bandwidth too.
Sure.
Actually, there's a bit of misunderstanding here. Minus 174 is got nothing to do with 50 ohms. It is an available gain per hertz. It's equal 10 log K.
He's right.
T is something like degree Kelvin. If it K is possible, this log becomes 1 K, then the power minus 38. If this log turns out to be minus 174 dBm per hertz.
For KTB.
It's got nothing to do with 50 ohms.
You're right.
You see? So therefore, this 50 ohm discussion, actually you're right. Because if you're using SAW filters, if SAW filter doesn't say 50 ohm termination, it doesn't work properly.
Yeah.
So the other thing is, all the measuring equipment has got 50 ohm failures. So in order to measure something, you have to rely upon the 50 ohm, because there's no other choice. But on the other end, when the direct matching of the amplifier to the antenna is under consideration, Professor Yaman is right. There's no need to have any matching.
Sure. This is also what I said for 60 gigahertz. For example, there where you are not forced by any SAW filter, you can do whatever you want. And the question is, we can put the question also in another way. How far are the optimum or the optimum noise resistance? How far is it from the 50 ohm, if you want to go with 50 ohm, from what is really what you have available given the frequency of interest? So if you are in some cases, it's not much far from 50 ohm.
See, I don't know that much. But as far as the most measurements are concerned, what we do is we short the input and bias and measure the noise voltage of the output. Then we short the output and we measure it as under the bias condition and you observe and measure. Then, of course, under these circumstances, we also measure the noise input without any signal application. So then we determine the minimum noise between the transistor, and based on the noise impedance of the transistor, the input and the output, and we try to
optimize the gain and the noise figure of the total system. Now, it's a long story. I don't want to make it
Okay. Okay, so moving to the transceiver architectures, yes. SNR is a given number, minimum. So
Why did we write its minimum, SNR as SNR minimum?
because this is what the standard specifies. Means that it requires this minimum SNR in order to elaborate in the digital processor in a correct way. Of course, you can use, that's the minimum acceptable. So if it's larger than that, it's okay. So this is the specification, minimum signal-to-noise ratio, which tells, given the noise figure, what is the sensitivity that you are required. Yes, yes, yes. Sorry? No, it's correct. Let's go to the architectures before entering into the design of the circuit blocks. Why do I do it? Because probably in this way we better appreciate why we use and make some choices about low noise amplifier, mixer, and whatever we will see. Because the first question we should have is the situation that we are going to face is several signals that are arriving at the antenna, and in particular, what we can describe it as a desired signal, then an adjacent channel, which is belonging to the same application, and maybe this is an alternate adjacent channel, and then at some point we will also have interferer outside. So this is what is arriving at the antenna of my circuit. So the first question is, before going into several details of the design, the first question is, wouldn't it be much simpler to immediately select the channel of interest at antenna and digitalize immediately and then process it? This would be the dream of Franco, probably. A digital A to D converter immediately? Not possible. Not possible, yes. A dream, but not possible. Why isn't it possible? Well, someone was thinking at some point we would have arrived because of the technology, but I think it's not possible. Sure. So why isn't it possible? Let's think about a simple example. We have, for example, a 900 megahertz received signal separated by a 900 megahertz plus 400 kilohertz tone, and so 400 kilohertz of separation, and we want to reduce by reject by 35 dB the alternate channel over the received channel, and we want to do it, for example, by means of a band pass filter, an LC second order filter. So if you make some calculation in order to be able to reject this adjacent channel by this quantity with an LC filter, you realize that the band pass should have a quality factor of around 60,000, which is not possible not only in an integrated fashion, but it's not possible not even with a really high quality off-chip discrete component. So this is why the first reason why you cannot, and the second would also that not only you would need a bandpass filter with a great quality, but this should be also tunable, frequency tunable, because of course you need to have it very precisely allocated, the bandpass, wherever you want. Anyway, this gives you a clear idea of why you cannot think about selecting a channel and down converting, and digitize it before making any other kind of operation. So the only thing that we can think about is band selection, which means that somehow we can use a band pass in between the antenna and the receiver and throw away the interferer outside the band of application, so still keep everything which is in a given bandwidth. For bandwidth, I intend the bandwidth, for example, of a GSM application or any application we can think for tens of megahertz, but we cannot think about separating 400 kilohertz at 900 megahertz. So we will keep the bandwidth and not the all together, and we will not be able to select anything inside that bandwidth, whereas we can start selecting something which is off the band of the application. So what we say is that we can do a band selection at RF, but we cannot do any channel selection at RF. So the first thing, at this point, we understand that we will do something on the received signal, which will not be selection, but some operation at RF frequency, and at some point we will need to translate and convert the received signal to a lower frequency. So at some point we will need an operation which is conversion to a lower frequency by means, for example, of a local oscillator. So the way the block look like, the basic block look like, is a received signal at RF, and at some point we will think about converting this signal to a new frequency where we will make some low-pass filter operation and then make it available for further amplification, selection, and conversion. So the key operation of any receiver is a conversion to a lower frequency in a architecture that in general, or when the circuits were not much integrated, was based on super heterodyne principles, and nowadays in these commercial CMOS products is more often based on direct conversion, as we'll see later on. Anyway, super heterodyne means that what we are doing is beating the input signal times, or beating with a local oscillator, which is a reference clock. In such a way, we translate the original frequency at omega in to around a new frequency, which is omega in minus omega low. And here you see the two sides of the spectrum, positive and negative. So omega in minus omega low and omega in plus omega low. If we are down converted, we are interested in the lower side of the spectrum. So we have understood we cannot select the channel at antenna, so we make some elaboration. In this elaboration, at some point, we will need to convert the band to a lower frequency where we will be able to perform this channel selection. So we are building our receiver from the needed function, which are conversion to a lower frequency, done in this way, where hopefully we will be able to make this channel selection that we could not do at RF. Why should we be able to make channel selection at a new lower frequency while we were not able at RF? Not for professor. This question is not for the professor. No, I made the question. I said, I made the question. So I said, the question does, the answer is not allowed to the professor. So not to you. You are not allowed to answer. No, I made a question. I said everyone can answer but you. It was a kidding. Okay. So why should we be able to select at IF and we were not able to select at RF? Yeah, because at lower frequencies proportionally easier because you need a lower Q, and at some point if you go to a really low frequency, you will be able to find quality factor that allow you to do it for sure off chip and also on chip operation. So this is the reason why we say we cannot select the RF, so we need to translate to make this operation. And so the thing we do is just band selection. So in principle, we could immediately convert the signal to a lower frequency and make this channel selection, but usually we use an amplifier which is assumed to introduce a low noise before the mixer, because usually doing this operation, the mixer introduces a significant portion of noise that we tend to counteract by means of the low noise amplifier. So the reason why, in principle, the low noise amplifier would not be needed if the mixer were not introducing much noise. But you cannot reduce this noise to a minimum with only a mixer, so you need a low noise amplifier which is supposed to increase the gain with a minimal introduction of noise. So the result you achieve in terms of noise when you apply a good low noise amplifier in front is much better than using only a mixer its own. So it would never be acceptable, the noise figure coming through an LNA-less commercial product. So this is how the architecture looks like. So we'll have an antenna, an output filter, and LNA for band selection. Then at this point, we will translate all the band at a lower frequency where we will be able to make a channel selection. We do this operation by means of a local oscillator on chip. So we know we are in a multi-user system, so we have several different users. For example, let's call them FRF1, FRF2, and then local oscillator. So the question is, how can we handle the different channel in this heterodyne architecture? We have at least two possibilities, because in one scenario, we can have a unique local oscillator at a given frequency and translate the input RF frequency RF1 to an intermediate frequency IF1, and then use the same local oscillator, the same frequency, and translate a second user, FRF2, to a different IF frequency, IF2. In principle, we could do it. Or, alternatively, we can use a local oscillator which is tunable and can be shifted in frequency, so that independent of the frequency at the antenna, RF1 or RF2, I convert the RF signal to the same IF intermediate frequency band. Okay? So usually, I would say always, designer do is opting for this second possibility, where you have a tunable on-chip local oscillator, which is easier to be done than thinking about having an intermediate bandwidth which is occupying a wide spectrum, which is basically the same spectrum occupied at antenna. So think about the filter at IF would be a filter with a very wide range, should span through the overall band of the application. So basically what the receiver does is tuning the local oscillator in such a way, whatever the RF frequency, this is always translated at the same IF. And this is at this IF that I concentrate my attention to design a good filter, good selective filter, and select this channel over all the others, or this channel over all the others. Whereas if I were carrying different frequencies, depending on the frequency at RF, the filter would be much tougher to be done. Okay? Okay, one thing that comes with the frequency conversion is the image problem or image rejection problem, because we have a desired signal, and then we make this operation. We multiply by a reference, for example, a cosine, and we downconvert the signal to a frequency which is, for example, omega low minus omega 1. But we know that cosine is insensitive to the sign of the argument. So if we look at the specular frequency, which is located in the opposite portion of the spectrum, but at the same distance, which we call omega image, we expect this same signal being converted just up on the received signal. So the scenario is that if we don't do anything, we use a mixer and use a cosine of omega law, we will have both the received signal and the image overlaid one on top of the other, with the result of a bad signal to noise ratio, because I confuse this signal, which is something I want to receive, with another signal, which is maybe even completely out of my application, out of my control, and this signal to noise ratio is can be destroyed, eventually lower than 1. Okay, so the thing that we are facing once building up this receiver is, on one end, we have the problem of selecting a channel. On the other side, we have the problem of rejecting the image. So these are the things we need to find a compromise between these two requirements. So in order to reject this image, what you do usually, especially when some off-chip components are allowed, is using an image reject filter. Usually this is off-chip, not in modern products. Used to be off-chip. Nowadays is also, again, if a direct conversion is there, things change. Anyway, if you use an image rejection filter, what you are doing is basically selecting this image over the received signal, so that basically the image reject filter has this kind of shape, so allows the received signal while rejects the image. But now the point is, if I were to choose an intermediate frequency, I should think about an intermediate frequency which is high in frequency, so that the distance between image and signal is larger, and I can reject the image in a good way. For example, let's assume that the IF is wide, so you see a good separation, at least higher than here. This is the shape of the image rejection filter, and what is the result is that at baseband we have the received signal plus an image, the residue of the image, but we also have an in-band interference approach. And the question can be, once I'm at IF, how can I go to baseband? What are the options? Because at some point I need to go to process the signal at baseband and give it to the digital processor. So in modern super heterodyne architecture, the second IF, so I have a first IF where I make all what I've been saying now, which can be usually the first integrated circuit transceiver used to have an IF at around 10% of the carrier. So if the carrier was 900 megahertz, the first heterodyne transceiver used to have a first IF at around 90 megahertz. Now, the question is how to go to baseband after this intermediate frequency. In modern super heterodyne architecture, this second IF is a DC to get rid of problems introduced by an eventual second image. So what I do, once I'm at IF, instead of going to another intermediate frequency for any other reason, what I do is making the channel selection and then moving immediately to baseband in order to avoid the problem of the image. Why do I avoid it? That's because basically signal and image are the same if I convert to DC, because the image and the signal are the left and right portion of the same signal. So if the signal is symmetrical, then the signal and the image are the same. So I have no problem to moving to immediately to DC. Okay? This opens to the possibility of thinking about, okay, so before going to such as an AM modulation, which keeps the shape of the spectrum symmetrical, because we can think about an AM modulation just as a multiplication in the time domain using a mixer. So we start from this spectrum and we result in amplitude modulation in a new spectrum. What I'm doing, I have the positive and negative sides of the spectrum. So when I convert to DC, what's happening is that I'm overlapping two different sides. Still, I have a kind of image rejection problem, even of the same amplitude, which is not true when I'm in a super heterodyne architecture where the other signal, the image, is maybe another application, can be several dB higher than the received signal. Second, it's not much tough to keep track of this information in the way you see here. So you are not forced. What you can do is instead of converting the signal all at once, you mark architecture directly to IF. This is one option for modern, highly integrated solution. A second option is going with a direct conversion directly to DC. In this spectrum, while in general, the advantages are, with respect to a super heterodyne, we do not have a true image rejection problem, just the so-called quadrature accuracy problem that I can tackle by means of this quadrature architecture. And there's also a second advantage. You can see here that we are using low-pass filter now because we are at baseband, and we are not using any band-pass filter. So why didn't people think about it before? Why it took quite a bit of time to introduce direct conversion instead of super heterodyne architecture? Alcatel.
Because of back to 1905, people tried to measure it. They made direct conversion and that didn't work. They consider simple RLC circuit, okay? However, if they want to increase the value, they introduce a loss. That's just like the
Francesco, are you going to have a practical session or you are going to
No, I'll continue.
With the